In previous presentations on fundamentals of electrical circuits, we've talked about OpAmp and using ideal OpAmp model to analyze a circuit without having to go to all the details of individual transistors within an OpAmp. A model that is somewhat more sophisticated, meaning that it gets you a little closer to the actual results you're going to see when you build a circuit with OpAmp, is called the OpAmp DC model. So in this case, you basically give up all the ideal OpAmp, forget about all the conditions that came from there, and what happens in a circuit, you literally replace your OpAmp with this diagram. So in other words, from Vin coming in, you're going to put an Ri. This stands for input resistance. And then on the output side, you go through a resistor, which we call the output resistance, and a dependent source, which the voltage is equal to the gain times Vp minus Vn. So if you want to analyze a circuit using DC model, you either have to go to the spec for the particular device you're looking for. For example, a lot of time we use LM324 as a starting place OpAmp, and the datasheet is available at engrcs.com if you want to read it more. And for that device, for example, Ri will be given as 2 mega ohm. Our out would usually be given as 75 ohms. And then A, the gain, the open loop gain, will be given as 10 to the power of 5. So this would be, if somebody told you use a DC model, assuming 325, you can literally use that. So what you do, you plug that into your circuit, and after that becomes a simple KCL problem to solve to find V out in terms of Vin. So this is called a DC model. Is a step more closer, if you will, not by much, but a step closer to actual results you're going to get from building the circuit than ideal OpAmp. As you're going to see, the amount of work required to get this additional close precision, it's significant. So you have to, for every problem, you have to decide, unless somebody asks you to do it, the analysis using DC model, then you have to use this. Or when they ask you to use ideal OpAmp, you have to use the 3 conditions of ideal OpAmp. But if they're giving a choice, you have to decide how important is it for you to be accurate. Is it worth the amount of effort that's required to do that? So now let's take a look at an example so we can kind of see how we apply this. So here I have an example set aside, a little bigger, which basically says, okay, we have this circuit set up, and they want you to find a V out here. They want you to find a V out using OpAmp DC model, and they're giving you the input impedance of 100K, output impedance of 100 ohm, and gain of 10,000. Frankly, this is a very lousy OpAmp, but nonetheless, we can apply it. That's good enough. We can apply that. So we want to apply this. Now, if I was doing ideal OpAmp, of course, would be a different path, but now they want me to use the DC model. And to do that, what we're going to do is we're going to go to draw. Let me bring the whole thing back a little better, a little more precise. So what we're going to do is we're going to replace the OpAmp with the model in here. So let's go see if we can get that done. So I'm going to have the V out still there, and then the V out will come in, and instead of the inside the box being ambiguous, the inside the box is going to be R out, and based on this we know R out is equal to 100 ohm. And then we're going to go to a dependent source, and we know 10,000 is the gain, so it's going to be 10 to the power of 4 Vp minus Vn, and then that goes to ground, and then this is Vn will be connected to Vp, and this connection is going to be through a 100K, which is 10 to the 5 ohms. Okay, so as you can see, let me use a different color here. So the OpAmp, basically, it replaces the OpAmp. Okay, but as far as we're concerned, just another electrical circuit we have to solve. So and then the V out also through a feedback resistor goes 10K, 10,000. Let's make it all ohms. 10,000 ohms comes to Vn, and from here 5,000 ohms goes through a 4K, and then this one goes through a 10,000, and it goes through plus and minus. So notice once we replace the OpAmp with this DC model of an OpAmp, it's really a simple circuit we have to analyze. And of course, for these kind of problems, the easiest way to analyze them is to use KCL or KVL. So there's nothing more than a simple KCL and KVL problem. So what we're going to do is let's go ahead and attempt to solve it. How many nodes we have? We have an essential node here. We kind of have this is not an essential node, so we don't have to worry about it. And then this is kind of an essential node, kind of not an essential. So these two are really not essential nodes if you look at it. So the only essential node you have is this one. And if you recall, I believe this was 1 volt and this was 4 volts. Take a look just to make sure. Yep. Okay, so all we need to do a KCL at Vn, and that will be Vn minus 4 divided by 5,000 plus Vn minus V out over 10,000. I suppose we can do that, but really it's not minus V out because V out is not an essential node. So we're going to do minus 10 to the power of 4 Vp minus Vn divided by 10,000 plus 100. So it will be 10,100. Okay, so and then we have to do one more. So we did this current, and we have to do one more current, which is the current going all the way down here, and that will be Vn minus 1 divided by the sum of these, which is 110 equal to 0. And this was Vp minus Vn. Okay, so now the question is, what is Vp? We can write Vp in many different ways. One of the simplest way would be to write a case. Typically we don't do this, but you can write a KCL for this non-essential node. If I write that, it would be this current is equal to that current. So basically I can say Vp, so I can do even though I don't have to do it, I do a KCL for Vp, and that's going to be Vp minus Vn divided by 100,000 plus Vp minus 1 over 10,000. Okay. Oops. Make it a little smaller so I have room to write more. And then the next thing I have to do is, so I've got 1, 2 variables, 2 equations. I can solve it, find Vp and Vn. But really what I was looking for is V out. So I can write another equation for this non-essential node. And if I write it for that non-essential node, it's going to be V out minus Vn divided by 10,000 plus V out minus 10 to the power of 4 Vp minus Vn divided by 100, and that's equal to 0. Now I've got three variables. I've got the Vout variable, Vp variable, Vin. I have three equations, and at this point it's pretty straightforward where you solve it and you're able to find Vout. So let's, instead of doing I'm going to let you solve the system of equations if you're interested in doing it. I'm not going to do it here. But let's, before ending this video, let's take a look real quickly as how we go about applying a DC model. So a DC model is typically, you replace the OpAmp with the Rout and the dependent source and Rin as is shown here. So you literally go to the circuit, take the OpAmp out, and put those replacements in there, and that's called it. And then after that is basically a simple KCL problem to solve and find Vout, Vp, Vn, and all of that kind of stuff.